that curves down. Similar on the other side. And then sort of symmetrical, then when you get to here, it's gonna look something like that. And then now I just need to make sure that this is sort of matching that one. We start out with a steep slope and then it goes to 0, so we start out with a high acceleration and it goes to 0. It's gonna have to curve in like that because I know this is flat down here. And then at this point right here, when you're stopping, when this thing's coming in and stopping, we've got potentially an issue right here. The problem stops just at the moment that the ball stops. What about the moment just after?
We don't care about it.
For the most part, we don't. However, the ball's coming in, it's caught. Does the person immediately turn around and throw it, or the person catches it and stops it? I can't remember the problem if I actually stated what happens there.
I think it stops.
I think it just stops, yeah.
I mean, it's going to stop if it turns around also.
Yeah.
Right.
The intent was it stops and sort of hangs there, which means that my acceleration at that point after G goes to 0. Which means that this curve here would have to
Go down.
come back down. It doesn't actually hit 0, but just gets infinitesimally close to it. And so if that's the case, then this line has to flatten out.
Okay.
And that is a crude sketch. And I don't know if I've mentioned the cough. Now, I know pandemic's going on, coughing is a sign of that. I've had a cough since January of 2020. So sometimes it flares up more than others.
That's
I've had a
long
cough
time.
since middle school, so.
Yeah. I was gonna get tested for allergies finally, but then I found out what my schedule was and I had to cancel it. So at some point, I'm gonna get it figured out. So I suspect it's probably just another medicine for life.
Yeah.
Or, you know, not wearing a mask all day, every day.
Well, I started the cough before pandemic.
Dr. Fox,
Yes.
you have described these graphs as being crude sketches, and I wonder if that is how we will describe our graphs when we do a test. Is this as accurate as we will get with like
Yes.
maybe, okay,
Yeah.
great.
The
Okay.
three main things I'm looking for, does it match what you have here? Is this the slope of that? Is this the slope of that? And are there any sharp points? Those are the three main things. Occasionally somebody throws in something that's really strange, in which case I'll then throw something else in. The problem ends at G, and some people at this point will then just keep going. You know, stop at G.
Just put a little star saying it. Crude sketch.
Right.
By the way, crude sketch.
And then later on, when I take off for something that you feel falls under the category of it's within realm of crude, you know, we'll come up, state your claim, make your argument. For a lot of things, I've usually thought through them by the time it gets there. You know, once I've graded 20 papers, I've thought through a lot of the eccentricities, but occasionally there's something I wasn't thinking of, and the student comes up and makes an argument, and I go, oh, I guess there was a different way of interpreting it.
Democratic, please.
Or what happens in some cases is I get about half of them graded, then I realize, oh, wait a second, that was a good interpretation of it. Let me go back and grade all those other ones again. All right, I'm about to get into the math piece of it. Wow.
You need some water or something?
Yeah, but I can't take off the mask.
You can't if you go to your office.
Yeah, you can go over. We'll be here.
I'll have time in 10 minutes, but we're finishing up lab stuff. All right. Constant acceleration kinematic equations. To To my knowledge, I'm the only person who calls them the cake formulas, but it stands for constant acceleration kinematic equations. There are four cake formulas. Occasionally there'll be a textbook which will throw a fifth one in there. I tend not to do the fifth one. It's just a variety of the others. But we'll start out with acceleration being the change in velocity over the change in time. This is not the cake formula, we're gonna manipulate it. If acceleration is constant, then it doesn't matter if this is instantaneous or average. If acceleration is constant, it's the same throughout the entire time. If in doubt, take some number, whatever number you want, for example 4, and then add however many 4s together that you want, and then divide by however many 4s you just did, and you'll still get 4. The average and the instantaneous values are all the same. So change in velocity is final velocity minus initial velocity. And I'm gonna do a little shorthand here, and I can't remember which way your textbook does it. Some textbooks do it, some do not. This is time final minus time initial, and I'm just gonna go ahead and say that my initial time is 0. I start the stopwatch at the beginning of the problem. Occasionally, it's not convenient to do that, but. So my thinking here is that my change in time is time final minus time initial, that's gonna be true. But if my initial time is 0, then my change in time is just time final. And well, now that I have only one time here, I don't really need the subscript anymore. And so it just morphs into t. So this becomes Vf minus Vi. There are a number of places where physics textbooks will do this, and some will do it, and some are very retentive about not doing it. When you get into electricity and magnetism, voltage and electric potential have a similar relationship like position and displacement. Voltage is, the difference is V final minus V initial, but a lot of textbooks will just use the letter V for it. At this point, what I'm going to do is I'm going to solve for my final velocity. And so I multiply both sides by time. So I have acceleration times time is equal to Vf minus Vi. And then I'll isolate Vf. So we have Vf equals Vi plus At. And that's the first cake formula right there. This is not set up and canonized, like Newton's first law is Newton's first law, no matter which textbook you ever look at, Newton's first law is always the same. The kinematic equations, this is usually the first one just because it's the simplest and it's usually the first one derived, but it's not canonical in the fact that if you went with the first cake formula, it doesn't necessarily have to be that one. But just to add fun, I'm going to write up a couple other variations of the exact same thing.
Can you say what KIC stands for again? It's
Constant acceleration kinematic equations.
Thank you.
And thus throwing the word formula after it is somewhat redundant, but I do it anyway. An ATM machine. All right. So I have Vf, just writing the same thing, equals Vi plus At. Also can be written as Vf equals Vo plus At. If you want to use O instead of I for the initial. You could also do Vf equals Vi or Vo plus A delta t. If I had not done this, we'd have a delta t here. And also, since this is the velocity at whatever the time t is, sometimes you'll also see V equals Vi or Vo. I'll stick with I for now. And then just drop the subscript next to the final one. This is the instantaneous velocity at some particular time t.
And these are all used to find velocity.
Yeah, all four of these equations and variations thereof, all are identical, it's just different textbooks do it differently, and the way I write it on the board might be different from day to day. But this is the essence, we have the velocity at some particular time t is equal to the initial velocity plus acceleration times however much time it took place.
Okay.
So I have a velocity time graph. Oh, I'm rushing through, just because everyone understands perfectly, but in case not, any questions?
What, are we gonna get into applications of what we're gonna use this for?
Oh, absolutely.
Okay.
Okay, yeah, I was gonna say, that's what I'm confused.
Yeah, I tend to drive them all and then do the applications. You want me to do applications as I go?
No, we can do whatever. I'm just wondering. Like, I don't wanna just learn an equation and then have a problem later and not know what to plug in.
Well, that might happen too, but we will go over the.
Yeah,
All right.
great.
So if for a constant acceleration, I've mentioned several times, acceleration is the slope. So if acceleration is constant, that's basically what my graph would look like. That's initial velocity and final velocity at some time t. Now this is a physics versus math thing here. This is my time axis and symbolized by the letter t. And then I have some time here symbolized by the letter t. The math purists, this is going to drive them crazy because my axis should not be the same as a particular value of time. Just, if you're one of those people, just get used to it. It'd be t sub f if you need to put a subscript there. So the two questions that we'll have to wait till, I guess, next Friday. A long cliffhanger.
Do we not have class on Monday?
Labor Day.
Yeah.
Holiday.
Yeah, okay. I was just curious.
It doesn't mean you can't study physics, but
Well, yeah.
What, then she can't show up?
well, the doors might be locked, but you can still come. And so the two questions are, how do we find average velocity and what is the displacement? So that will be the cliffhanger. At this point, some people will still needed to wrap up some of the stuff from Friday, Wednesday, whatever that last time was. If you don't, then have a safe weekend, but if you do, you've got 20 minutes officially left for class. I'll pull out last lists.
That subscript on that D at the top of the green,
This one?
that's over
On the graph.
down on the green on the graph.
Oh, that's enough.
That's enough.
I guess I should put that by variations of what S looks like.
Get used to it.
I really need to get back to teaching elementary school the right idea. So I'm gonna stop this before someone really embarrasses all of us.